Here's yet another example of a gear pump. This is a Prince SP25A32. There's really nothing external to quickly distinguish this as a gear pump other than the part number. The drive shaft is visible on one end, as well as two ports on the other. The large port is intended to be the inlet, and the small port the outlet. The bolts can be removed and the port or back end plate taken off. We can take the drive or front end plate off. Note the static seals on both end plates. Inside the housing or body, we can see a bearing carrier assembly holding the intermeshed drive and idler gear. We can remove the bearing carrier assembly and wear plate. Now we can get a good look at the intermeshed gears. We can pull out the back bearing carrier assembly and wear plate and the drive and driven gears. There you have it, a fully disassembled gear pump. Truly horrifying in its complexity. The manufacturer's service manual for this particular pump includes a great exploded diagram, as well as disassembly and reassembly instructions, inspection procedures, and troubleshooting advice. Here's the housing. There's a faint tracked area matching the gear position. However, note the tracked area is smooth and there's no unusual scoring or pitting. Here's the drive gear. The teeth aren't pitted, warped, or broken, nor is the shaft bent. Same thing for the idler gear. The teeth aren't pitted, warped, or broken, nor do they show any unusual discoloration. I'm not sure if you can really see it with this picture, but the teeth of both the drive and idler gear are asymmetric, in that one side of a tooth is smooth and the other side has a tiny undercut. The orientation of this undercut is super important when reassembling this pump, as is the orientation of the bearing carrier assembly. The manufacturer's service manual includes a diagram showing the proper orientation for different rotation directions of the prime mover. When reassembled, the gears should not bind when rotated in the correct direction. The pump datasheet includes some important specifications. The SP25A32 has a displacement of 2.008 cubic inches per revolution and is rated for 3000 psi. Additionally, the datasheet specifies the permissible viscosity range and filtration level, in this case 1714. The 2-number ISO cleanliness code indicates this gear pump could essentially care less about particles in the 4-micron bin and concerns itself only with 6 and 14 micron size contaminants. The pump datasheet also includes performance data in a tabular format rather than a chart. Note the performance data is based on certain standard conditions, specifically an oil with a given viscosity and temperature, 140 seconds universal at 120 degrees Fahrenheit. Given ideal conditions in which a pump with a displacement of exactly 2.008 cubic inches per revolution is driven at increasing rotational speeds, we'd expect the flow rate to increase linearly like the ideal curve in green. When the actual performance data from the table is plotted on the red curve, the pump behaves as expected. At an increased pressure requirement of 3000 psi, flow rate is slightly reduced due to increased leakage. The theoretical versus actual performance data could be used to calculate volumetric efficiency at different rotational speeds and pressure requirements. For example, when a pump with a displacement of exactly 2.008 cubic inches per revolution is driven at exactly 1500 RPM, one would expect it to produce a flow rate of 3012 cubic inches per minute, or approximately 13 gallons per minute. However, the datasheet says that when operated at 3000 psi, the pump only actually produces 12.43 gallons per minute, or approximately 2,871.3 cubic inches per minute. Assuming rotational speed really is exactly 1500 RPM, we can solve for displacement per revolution to be not 2.008 cubic inches per revolution, but rather a slightly smaller, approximately 1.914 cubic inches per revolution due to increased leakage. Volumetric efficiency at 1500 RPM and 3000 psi is therefore 1.914 over 2.008, or close to 95.3%. Additionally, note this pump datasheet also includes required mechanical power input for different rotational speeds. This data could be used to calculate overall efficiency of the pump. where overall efficiency is the ratio of hydraulic power output for a given quantity of mechanical power input. Hydraulic power can be calculated in units of horsepower by multiplying pressure in units of psi times flow rate in units of gallons per minute and dividing by 1,714 to account for constants. For example, the hydraulic power output for a pump producing 12.43 gallons per minute at 3,000 psi is approximately 21.76 horsepower. The datasheet specifies the pump must consume at least 24.22 horsepower of mechanical power input when operated at these conditions. Overall efficiency is therefore 21.76 over 24.22, or approximately 89.8%. Overall efficiency includes not only volumetric inefficiencies, but also friction, heat, any misalignment between the prime mover and pump, and or play between the mechanical linkages, among other losses. Moving on, here's yet another example of a gear pump. Note the suction strainer on the inlet of the pump prevents it from ingesting any contaminants in the reservoir that can clog the inner workings. Additionally, note the bottom plate includes an integrated pressure relief valve. When we pull off the integrated pressure relief valve and disassemble the housing, we find two equally sized intermeshing gears, where the drive gear is permanently affixed to the drive shaft, and the driven gear sits in two recessed pockets in the housing. Note these gears are helical rather than spur gears in our last example. The helical cut allows for increased contact surface area and decreased noise. Given the tiny gears, we probably expect small displacement value per revolution. This particular gear pump is actually employed for an oil pumping application, not a high-pressure hydraulic system. However, a quick look at the datasheet serves our purposes quite nicely. This particular pump is a Rickmeyer R25 2.5, where 2.5 means it has a displacement of 2.5 cubic centimeters per revolution, or roughly 0.153 cubic inches per revolution. It's super tiny. The common place of the decimal point is kind of a European thing, like fast trains, free healthcare, and smoking teenagers. Note the datasheet is written in both German and English. Don't be surprised one day when you open up the box housing a new part and find a datasheet or instructions written in a language you can't read. My advice is to deal with it. Numbers and charts are universal, and you should be smart enough to interpret what you see. The units might be a little odd for those cave-dwelling savages that don't use the metric system. However, a simple unit conversion should do the trick. The flow rate versus pressure graph looks exactly like the curve we examined in the hydraulic pumps lecture. Given a nominal drive speed, as pressure goes up, flow rate goes down. This behavior can be largely explained by increased leakage and the tendency of the prime mover to rotate slower given increased torque requirements at higher pressures. Note pressure differential between the suction and pressure connection is expressed in units of bar. Obviously, this pump isn't meant for super high pressure applications since the curve ends at 10 bar, or roughly 145 psi. Flow rate is expressed in cubic decimeters per minute, which might seem odd at first until you realize a cubic decimeter is actually a liter. This unnecessary coyness with the units kind of makes me want to punch this datasheet in the face, but I am not going to win any hearts and minds raging about proper units given my country of origin uses gallons, circular mils, degrees Fahrenheit, and half the population doesn't believe in dinosaurs, yet they do believe in angels. The struggle is real. Regardless, flow rate varies from just high of maybe 3.6-ish liters per minute to just low of maybe 2.7-ish liters per minute inside the recommended pressure range. Note the chart is again based on certain standard conditions, particularly a nominal drive speed of 1450 RPM and a liquid with a given kinematic viscosity of 33 square millimeter per second. Again, the viscosity units are unnecessarily coy since 1 square millimeter per second equals 1 centistokes, another common viscosity unit. 33 centistokes, by the way, roughly equates to a liquid with a viscosity of 155.7 Seybold seconds universal. roughly that of hydraulic oil. Allow me to step out of pump world and briefly comment on the prime mover. Note the nominal drive speed, 1450 RPM, is characteristic of a 2-pole pair per phase squirrel cage induction motor operated at 50 Hz, as is common in the EU, not the 60 Hz standard employed in the United States. A 3-phase AC system at 60 Hz might see a 2-pole pair per phase squirrel cage induction motor rotated around 1740 RPM, thereby skewing the flow rate curve upwards, given this is a fixed displacement pump operated at increased rotational speed. Lectures on motors and generators will discuss how pole pairs per phase and excitation frequency affect synchronous speed, the speed of the rotating magnetic field for 3-phase AC systems. Additionally, the datasheet for this pump family lists the permissible viscosity range, permissible degree of contamination using the ISO cleanliness standard, in this case 21-1917, as well as temperature ranges for 2 available types of seals. Before we bring this lecture to a close, as much as I'm about to roll my eyes right out of my sockets, in the interest of thoroughness, I should at least briefly introduce Lobe, internal, and gear rotor types of gear pumps so you can compare them with external gear pumps. External gear pumps, as the name implies, are those pumps characterized by gears with teeth radiating externally away from the body, like the spines of a porcupine. A Lobe pump, for all practical purposes, is an external gear pump, except it uses rounded lobes instead of angular teeth. If you know how an external gear pump works, you know how a Lobe pump works. Internal and gear rotor type gear pumps, in contrast, use internal gears, where the teeth radiate inwards like the teeth of a shark. Both these types of pumps feature a rotating, internally toothed gear surrounding a rotating, externally toothed gear, kind of like a shark eating a porcupine. The internal gear pump uses something called a crescent seal to create a seal between the offset gears, whereas a gear rotor pump does not have a crescent seal and instead relies on a rotor with one less tooth and an offset port plate to positively separate the input and output. Here's the inner workings of a gear rotor type hydraulic motor, where a hydraulic motor is essentially the opposite of a pump, being an actuator that produces rotational mechanical power when supplied fluid power. Note, external gear pumps have a reputation for being extremely tolerant of less than clean fluid because of their relatively simple construction. After all, there's really only 2 moving parts, the drive and driven gear. For this reason, external gear pumps are reliable, robust, and inexpensive. However, not exactly the most mechanically efficient pump, nor suited for extremely high pressure applications. Later lectures will examine vane and piston pumps that exhibit notable differences in construction, operation, and performance. Until then, that's all I've got for you. In conclusion, this lecture discussed a common fixed displacement pump used to provide pressurized flow to hydraulic systems, known as a gear pump. We discussed the concept of operation, examined the internal workings, identified constituent parts, and looked up pertinent data on a datasheet. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.